In this practice paper, I've made some hopefully quite challenging questions, so if you're aiming for an A star, then these are definitely for you. We'll jump straight in with question number 1. In question 1, we are shown a diagram of a function. We're not told what the function is, but we're told it's got some asymptotes at y equals 3 and x equals 2 and x equals 0. The turning points and the point where it crosses the x-axis, they're shown on the diagram. So 1, 1, 3, and then 5, 3 point whatever here. And then the actual question is, sketch the graph of y equals f dash of x. This is one of those topics that is in the AS book that people seem to forget about. This is sketching gradient functions, because f dash of x, that's the gradient. How are we supposed to know the gradient if we don't even know what the function is? Well, we know if it's increasing or decreasing, don't we? If we look at the first half of the graph, it's going up, 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 up. It's increasing. Therefore, the gradient must be bigger than 0. So the first half, we know it's going to be in the top half of the diagram. Increasing means the gradient is bigger than 0. Bigger than 0 means above the x-axis. What about in the next section? Well, it's coming down, 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 until we get to 1, 1, and then it goes back up. So we know until the point 1, it must be negative, so it must be below, because it's decreasing, and it's a negative gradient, so it's below the x-axis. But after 1, it's bigger, it's increasing, it's going to be above the x-axis, until it gets to that asymptote there at 2. We'll think about what happens at the asymptote later on, but what's happening for the rest? Well, again, it's increasing, up, 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 until 5. So we know that until 5, it's going to be above, we don't know where yet, but it's going to be above the x-axis, because it's increasing, gradient bigger than 0. And then finally, from 5 onwards, it's going down, so we know it's going to be somewhere down here. So that's the first thing I would check. Positive or negative. Maybe you could draw some vertical lines if you wanted, just to separate them out, but you don't have to. Okay, next thing I would think about, definitely the stationary points. If it's a stationary point, what's the gradient? The gradient 0. So that means that this point 1, it's not just going to be above or below, it's going to cross there specifically. Where's the other stationary point? It's over here at 5. So it's going to cross. Is it going to cross anywhere else? No, because there's no other stationary points. We do notice, however, that this is very close to being stationary. It's not actually stationary, it's not actually flat, but it's an asymptote. It's very, very close to being flat. So what we could do is we could put a little x just above the x-axis, just to say it's really, really close to 0, but it's not quite 0. Same thing over here, is really, really close. And this time I'm going to put the x just below because it's decreasing. We have to use rule 1. Is it positive or negative? Well, it's negative because it's going down. So let's put the x really close, but it has to be below. So the next thing I'd be thinking are stationary points. Or what about this gradient up here then? As we get closer and closer and closer to the y-axis, the gradient gets bigger and bigger and bigger. Well, what does that tell us? That tells us that the gradient must get bigger and bigger and bigger and bigger and bigger and bigger, like that. In fact, the asymptote here on the y-axis is going to be the same asymptote, again, on the gradient function. I'm not quite drawn that perfectly, but let's make that round out a bit more. So what about this next section then? The function's coming down, 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 so we know it's going to be in the bottom section. What's the gradient to start with? It's really, really steep, so it's going to be nearish here, down somewhere down by infinity. And we know that eventually it gets to 0, gets to a stationary point. So what's that going to look like? It's going to be an asymptote, and then it's going to come out to 0 at the point where it crosses, which is 1. Then what's going to happen? It's going to increase. If it's going to increase, it's going to be in this top section over here. What do we know? As we get closer and closer and closer to 2, that gradient gets closer and closer and closer to infinity. So we're actually going to get an asymptote at 2. What's happening next? We are increasing again until 5. So we know until 5 we're going to be in the top section. Is the gradient getting steeper or less steep? well, it looks like it's getting less steep to me. It's rounding out. It starts off pretty steep though, and then it rounds out. So it's going to start off pretty steep and then round out, come down to 0 on the x-axis. And then what's happening, it starts out flat and then it ends out flat. What's the only way to connect these two? It's just with a little line like that. So it comes down a bit, you don't know where. If you don't know the function, you can't work that out. Comes down a bit and then comes back as an asymptote towards the x-axis. If you struggle with these, what you could think about is it getting steeper? If it's getting steeper, it's either going up towards infinity or down towards negative infinity. So here it's getting steeper and steeper and steeper. So it's heading up to infinity. From 1, 1 upwards, it's heading up, it's getting steeper. So it's heading to infinity. But from, say, here to here, it's getting less steep. That means it's coming from infinity downwards, getting less steep. So just one way to think about it. And one last hint about these is any vertical asymptote stays in exactly the same place, while any horizontal asymptote will always move into the x-axis. All right, question 2 is a bit of trig. We've got cosec x over cosec x plus 1 plus sec x over sec x plus 1, and we need to show it's equivalent to this monstrosity written on the right-hand side. The first thing I'm thinking is that what's on the right-hand side only has one fraction, so we somehow need to combine it together. The second thing I'm noticing is it's only got sines and coses in, and there's no cosecs or secs. So there's two things we can do. We could either put them together as a fraction first, and then sort out the sines and cosines, or we could sort out the sines and cosines, and then put them as a fraction. I'm not sure it matters which one to do. I will turn it into sines and cosines first. We'll see what happens. So cosec is 1 over sine. So it's going to be 1 over sine over 1 over sine plus 1, plus 1 over cos plus 1 over cos over 1 over cos plus 1. Now, if you're not used to dealing with triple/quadruple fractions, the best way to do it is think about timesing the numerator and the denominator by the same thing, which will cancel out the thing you don't want. So here, I'm going to times this by sine x and this by sine x. And then I'm going to times this numerator by cos x and this denominator by cos x, treating it as a bracket here and a bracket here, of course. So we're going to get 1 over sine times by sine is just 1. And then 1 over sine by sine is just 1. 1 times sine is sine. So again, imagining those brackets there. That looks a lot simpler to me. Next thing we can do over here, exactly the same. 1 over cos times cos is 1. 1 over cos times cos is 1. 1 times cos is cos. Already looks a lot better. Now it's in terms of the sines and the coses, but it's not all together in one fraction. So let's do that. We need to get a common denominator, so we're going to cross multiply. So 1 plus cos x plus 1 plus sine x over 1 plus sine x, 1 plus cos x. And that's going to be, basically the answer. I'll let you finish off adding 1 plus 1 to get 2. And now on to part B. I've just quickly changed the wording there so it's a bit more obvious what I'm looking for. So we're trying to find a similar expression, and by that I mean an expression where the right-hand side matches up with the denominator of the right-hand side in part A. Now, as before, if I see sec, I'm going to write it as 1 over cos, and if I see cosec, I'm going to write it as 1 over sine. So I'm going to get this pretty funky expression with a lot of 1 over sines and 1 over coses in it. But that's okay because we're going to be able to sort that out. If I times both numerators and denominators by cos x here and here, and by sine x here and here, then we'll get something which is a bit nicer. We'll get something that only has 3 fractions, 3 layers of fractions rather than 4. 1 over cos times cos is 1. 1 over sine times cos is cos over sine. And remember that there's brackets there, So this is 1 times cos, which is cos. The second fraction, 1 over sine times sine, is 1. And then 1 over cos times sine is sine over cos, with 1 times sine being sine. It's still not exactly what we want because there's still a fraction that's 3 layers down. So the next thing we can do is times by sine over sine and times by cos over cos in the right hand side. This is going to delete that triple fraction because we're timesing by the denominator. It's going to cancel each other out. If we continue this then, 1 times sine is going to give us sine. Cos over sine times sine will just give us cos. And cos times sine will give us cos x sine x. Similarly, over here, we're going to have sine over cos times cos, which is sine. Sine times cos is sine x cos x. From here, what I'm looking at is, I'm thinking about the denominators. We want the denominator to be sine x plus 1 and cos x plus 1. Well, we might notice that if we factor out a cos here, then this is 1 plus sine x. Seems pretty handy. And over here, if we factor out a sine x, we get 1 plus cos x. Seems pretty handy. What we can... hopefully you spotted that. What we can now do, using the extra hint, since I've changed the question, we don't want the cos there because otherwise the denominator is not going to be the same. So we can rewrite this as sine x over cos x over 1 plus sine x, and cos x over sine x over 1 plus cos x. So the denominators are now matching up. But you may be thinking, well, why have you just got a triple fraction? You didn't need one. But sine over cos, that's equal to tan. So yes, you can write it as a triple fraction, but you can also use the definitions of tan, and over here it's going to be cot to write it in a nicer form. Finally, what we can do from there, we can cross multiply and get some common denominators. So I'm going to times tan by 1 plus cos and cot by 1 plus sine. And then the denominator is going to be 1 plus sine x, 1 plus cos x. And then I'm probably going to simplify that a bit. 1 times tan x is tan x. Tan x is sine over cos, so times by cos we're going to get sine. And then cot is cos over sine. So when we do cos over sine times by sine, we're going to get cos. All of that divided by 1 plus sine x, 1 plus cos x. As I wrote this question, I'd give marks for probably any of those 3 last lines. Okay then, why did we bother going through all of that working? What are we actually going to do with this? This is for part C. Hence, or otherwise, but probably hence, show that the solutions to this equation, this really big equation, satisfy tan of x equal 1. Basically what that means is, once we solve this, the solutions to that long equation should be the same as the solutions to tan of x equals 1. What you should notice is that the left-hand side is exactly the same as part A. So the left-hand side is going to be the same as sine x plus cos x plus 2 divided by 1 plus sine x, 1 plus cos x. Change the order of the 1 and the sine x, doesn't matter too much. And then on the right hand side, what do we notice? This is the same as part B. So what I'm going to write on the right hand side is that this is equal to tan of x plus sine of x plus cot of x plus cos of x divided by, and then I'm going to do the same denominator, 1 plus sine and then 1 plus cos. So that's this down here, what we just found from part B. Do you notice anything now? Denominators go whoosh, whoosh, swoosh, swoosh. And we can say that sine x plus cos x plus 2 is going to be equal to tan x plus sine x plus cot x plus cos x. But there's a sine x over here and a sine x over there. We can say goodbye to them. Same for the coses. Goodbye. And we're left with tan of x plus cot of x is equal to 2. Shaping up quite nicely so far. We're not quite there though. How are we going to get the answer in terms of tan? You've got to remember that cot is already in terms of tan by definition. So tan of x plus 1 over tan of x is 2. Guess what this is? It's a hidden quadratic. Of course it is. It has to be. Times everything by tan of x. We get tan squared x minus 2 tan of x plus 1 equals 0. That's a lovely quadratic. Tan of x minus 1 squared equals 0. Tan of x is equal to 1, smiley face. And the next question is about sequences, arithmetic sequences. When I see this, I'm thinking that I don't know much about the sequence, so if I find the first term and if I find the common difference, then surely that's going to be helpful. The first term is going to be equal to 2. That's because it's when n is equal to 1, because it's the first term. The common difference is going to be equal to minus 2, and that's because it's of that form. Remember, the common difference is the d in a plus n minus 1d. So in the formula there, it tells us that must be d here, which is minus 2. So what's this question asking for then? It's asking for the sum. So we're thinking Sn, and it's asking for the sum of the sequence, but with weird limits from n plus 1 to 2n. If it doesn't make sense to you, try and imagine that with numbers. Imagine if you wanted to find the sum of the sequence from r is equal to, let's say, 11 to 20. How would you go about doing that? Well, you'd need to sum up all the first 20 terms of the sequence, and then you'd need to minus the first 10, because you don't care about them. Well, it works in exactly the same way. We want to sum up the first 2n terms, S2n. What do we want to get rid of? We want to get rid of the first n. We don't care about them. But we know the formula for S of n. The formula, remember, is n over 2, 2a plus n minus 1d. Now, you probably know that's in the formula book, but A-star students usually are able to remember formulas such as this. This is Sn, though. This is S of 2n. So what you'd have to do is you'd have to sum in the 2n. So 2n over 2, 2a plus 2n minus 1d. What are we subtracting? We are subtracting just Sn, so we're subtracting all of this. Do we know what a is? Well, yes, that's what I wrote at the very, very beginning. So let's do a bit of simplification. 2 divided by 2 is going to cancel. 2 lots of a is 2 lots of 2, which is 4. And then d is minus 2, so that's going to be minus 2, 2 and minus 1. Over here, 2 times a is still 4, minus 2 n minus 1. And then we go through the motions. We cancel things down, we simplify, and hopefully we get what's given in the question. So just to check, 3n brackets 1 minus n, which matches up with what it says in the question. There's lots of steps there. You can probably skip some of those steps as just writing it out to make it super clear which steps I'm taking. Right, 2 proof by contradictions. The first one is proving that the logarithm base 3 of 4 is an irrational number. If it's a contradiction, remember that you've got to assume the opposite. So why don't we assume that the logarithm base 3 of 4 is the opposite of being irrational, which means it must be rational. Or, if you want to use the proper notation, the blackboard Q. If it's rational, what does that mean? It means it can be written as a fraction. So that means log base 3 of 4 can be written as, well, I'll go basic, a over b. Could have done p over q, x over y, whatever floats your boat. There's one more thing we have to mention here, and that is a and b are integers. And we cannot have b is equal to 0. That would cause some issues. What are we going to do from here? We've got a logarithm. How do we work with logarithms? Well, let's see if we can just get rid of the logarithm. Then we're working with powers, something that we're more familiar with. So remember, base answer power in that order, BAP. So the base is 3, the power is over here, is A over B, and the answer is equal to 4. Well, if this is true, let's see if we can rewrite it. This is 3 to the power of A in a Beeth root, which is equal to 4, using our laws of indices, which makes it easier to see that if we raise both sides to the power of B, then 3A will be equal to 4B. Is there anything here that's looking odd? Can you think of any numbers A and B for which this is true? The only solution is in fact A and B are both 0. Because this is always going to be a power of 3 if A is bigger than 0. This is always going to be a power of 4. There are no powers of 3 and 4 that match up unless A and B are 0. So the only solution is A equals B equals 0. But wait a minute, now you might see the contradiction. This is a contradiction because we assumed right from the beginning that B was not 0, but we've just found out that B must be 0. It can't be equal to 0 and not equal to 0 at the same time. Therefore, that's a contradiction. Therefore, that logarithm base 3 of 4 must be irrational. What about the second contradiction then? I've quickly changed over the 4 and the 2 because otherwise it doesn't actually work, but we're trying to prove that there are no integers x and y such that 4x squared minus 3y squared is equal to 2. So what's the assumption going to be at the very start? We're going to assume the opposite. If you want to assume the opposite of there are no integers, then you are assuming that there are integers. So you're assuming that this statement is true for some integers x and y. But where's the contradiction going to come from? Well, what we have to notice for this one is that there are some even numbers and some odd numbers. So what I'm actually going to do is I'm going to rearrange slightly and say 4x squared minus 2 is equal to 3y squared. Now, of course, 4 and 2 are both even, so this whole side must be even. But 3 is odd, which is odd. Therefore, this implies that y squared itself must be even. And if y squared is even, then y is even. And if y is even, how can we write it? We can write it as 2 lots of, let's call it k. If we know that y is equal to 2k, then let's pop that back in the original equation and see what happens. Like this. So we're going to get 4x squared minus 2 is equal to 12k squared. And now what I'm going to do, I'm going to divide by 2. 2x squared minus 1 equals 6k squared. And now we might see the contradiction because we've got an even number here and an odd number. So this whole side is odd, but this side is even. So this is our contradiction. This is an odd number is equal to an even number, which of course is never true. That's our contradiction. Therefore, what I'm going to say, I'm going to copy and paste the question again. There are no integers x and y such that the original assumption 4x squared minus 3y squared equals 2. Number 5, I made as a bit of a funky question, as you might be able to see there, but I just thought the final answer was quite a nice result, so I thought I'd keep it in. Part A, just 2 marks, we're just verifying, so that means just shove it in and hope it works. So we're trying to verify that x equals 1 is a solution to that whole thing equals 0. So let's sub in f of 1. So we're going to get, in a big bracket, 2 log 1 plus 9 over 1, that whole thing squared, minus 5 log 1 plus 9 over 1, plus log 10. So that's going to be 2 log of 1 plus 9 is 10, and then that's going to be squared, minus 5 log 10 plus log 10. That's 2 lots of, well, log 10 is actually just 1. So 2 squared, which is 4. 5 times 1 is 5, plus 1 this is equal to 0. Therefore, write the little conclusion, x equals 1 is a solution to f of x equals 0. Okay, now for the funky bit. Now we need to find the other solution and give it of that form, which is a very strange form. So what I'd like you to notice here is that we've got log of x plus 9 over x with a square and log of x plus 9 over x. So, ringing bells that it's a hidden quadratic. The first thing I would do though is I would expand that first bracket just to write it as 4 lots of log x plus 9 over x squared like this, minus 5 of the same thing, plus log base 10. Just because then it's really in the form for, let's say, y squared minus 5y plus a number equals 0. Now you don't have to make y equal to this, but it does make it easier to see. So if y is equal to logarithm of that, then we've got 4y squared minus 5y, and I'm going to do plus 1 because it's log 10. And we'll try and put this into brackets. I'm going to have 4y, y, 1, 1, 1, minus, minus, there we go. 4y minus 1, y minus 1. This one should make sense. Should it make sense? I was going to say this would make sense. X equals 1 would make sense. Y equals 1 is the solution here, or y is equal to a quarter. Let's see what x should be. So y equals 1. That means that log of x plus 9 over x is equal to 1. Rearranging using the laws of logarithms, we get that x plus 9 over x is equal to 10 to the power of 1, or, just 10. So x plus 9 is equal to 10x. 9x is equal to 9. X is equal to 1, which I didn't expect y to be equal to 1 and x equal to 1, but x is equal to 1 makes sense because that's what we got in part A. Let's find the other one then. If y is equal to a quarter, then log x plus 9 over x is equal to a quarter. Raise both sides like this. 10 to the power of the left, the log disappears. 10 to the power of a quarter, we get this. In exactly the same way, I'm going to times both sides by x, like this. And I want x, so what I'm going to do is I'm going to subtract x from both sides like this, which we can then rewrite as x lots of 10 to the quarter minus 1, like this. Therefore, we can say x is equal to 9 divided by 10 to the power of a quarter minus 1. So that's not in the form that it gives, so we have to do a bit more wacky stuff. So imagine like it's a rationalizing the denominator, square root. Why don't we try and times by 10 to the power of a quarter plus 1, see what happens. In the numerator, we're going to get 9 lots of 10 to the power of a quarter plus 9. And in the denominator, this is a difference of two squares. So it's going to be 10 to the power of a quarter times 10 to the power of a quarter, which is 10 to the power of a half. Ignore all the middle terms, they will just cancel out, and it's going to be minus 1. It's still not in the form that's given, so what can we do? We can times by 10 to the power of a half plus 1 over 10 to the power of a half plus 1. Again, in the denominator, this is difference of two squares, so it's going to be basically square root 10 times square root 10, which is 10, and then minus 1. In the numerator, I'm actually going to leave it like this for now because I noticed it will cancel out. 10 to the half plus 1, like this. 10 minus 1 is 9. 9 divided by 9 disappears. You just about see that over there. And we're almost done. 10 to the quarter plus 1 times 10 to the half plus 1 is equal to, add the powers, 10 to the 3 over 4, plus 10 to the half from these two, plus 10 to the quarter, plus, it's 1, but I'm going to write it as 10 to the 0 just to complete the pattern. So therefore, we have written it in the form 10 to the power plus 10 to the power plus 10 to the power plus 10 to the power. And if you notice, that's an arithmetic sequence going down by a quarter each time. which at least in my opinion is pretty cool. In question 6, I've written a question where you can't just use the calculator to answer it for you. You have to use the actual maths because it's in terms of a and b. So we've got a quadratic, so you've seen plenty of quadratics. X minus a, x minus b. I'll give it a little sketch. We are told that a and b are integers, and a is bigger than b is bigger than 0. So that means the roots are going to be a and b, and a is going to be further along the x-axis than b. Because it's a quadratic, we can go like this and fill it all in. The other thing we can find if we want to label our graph is we can label this point here. That's when x is 0 because it's on the axis, so therefore a times b. Now the range of f of x, something that trips up a lot of people. How low does the graph go and how tall does the graph go? Well, we can see the lowest point is right there. So we need to find that point. How tall does it go? I mean, it just keeps going on forever and ever and ever. So there's only going to be this one point, and we can just say y, or f of x, is bigger than that, then we're sorted. What point is that? It's the turning point. How do we find the turning point? Well, there's a few ways of doing it. What I'm going to do is I'm going to expand f of x to get this, and then I'm going to complete the square. So we're going to take x squared. Sorry, I was trying to do it all in one go. So x squared minus a plus b x plus ab. When we're completing the square, we take that thing and we divide it by 2, square the bracket, and then minus all that thing squared. So we're going to square the numerator and square the denominator. And then we can't forget about the ab, little ab on the end. When you've completed the square, yes, I'm sure you can probably rewrite that in a different form, but I'm not going to bother. You can almost just pluck out the turning point because the x coordinate is just this, with the minus taken away. So a plus b over 2. And then the y coordinate is just this at the end. And in fact, I'm going to write it as this because then it looks a teeny bit nicer. So that's the turning point. What's the range then? Well, f of x is above that point, so it's bigger than or equal to. Bigger than or equal to because it can get down there. It's not like it misses it. And then, yeah, just copy this down. And that's it. That's the range of f of x in terms of a and b. As with some of these other ones, part b gets a bit funkier. We're now told that the range of 1 over f of x is given by this set here. f of x is less than or equal to minus 1, or f of x such that f of x is bigger than 0. Let's try and work out how we'd even draw 1 over f of x, because that's going to be the key to this problem. If we've got the original graph like this, then we think about all the different points that we could do 1 over. What about 1 over 0? Well, I don't fancy doing that because it's going to give an asymptote. 1 divided by 0 is going to give this infinite answer. So anytime that you do 1 over and it's 0, it's going to produce an asymptote. So there's going to be an asymptote over here as well. What about when f of x is really, really big and you do 1 divided by it? What's going to happen? 1 divided by a really massive number, that's now 0. So it's like the opposite. 0 goes to infinity, infinity goes to 0. So what's going to happen is all this curve here that's going up to infinity is going to go completely the opposite way and become an asymptote, like that, against the x-axis. Same over here. What's going to happen over here? Well, the point B and the point A are going to be asymptotes. So the curve is going to start really low at minus infinity here and here. What's the only way to finish it off? Well, the only way is to connect them together. Now, if I compare this against the set that's given, it's less than or equal to minus 1, or it's bigger than 0. Let's look at the top half. That curve here and here is already bigger than 0. So this bit is kind of taken care of. The important bit is really this one. We are told that this range is less than -1. So that means that this point here has to be -1. But we don't know the coordinates of that. All we know is the coordinates of that point there on the original. But we can just do 1 divided by it and find the actual answer. So if we know that this coordinate on the original curve is this point up here, then if we do 1 divided by that point, which looks a bit messy, that should be equal to -1, this point on the new curve. In the question, we're also given the information that b is equal to 1, so that should simplify things for us. So let's see, we're going to get 1 over a times 1 is a, and then a plus 1 squared over 4, which is equal to -1. I'm going to come over here. I'm going to times both sides by this denominator because I don't fancy dealing with that fraction. So all of this is going to be times by -1. So minus a and plus a plus 1 squared over 4. Times everything by 4. 4 is minus 4a plus, I'm going to expand that bracket as well, a squared plus 2a plus 1. And then I'm going to get everything on one side. I'm going to get a squared. And then these will simplify down to minus 2a. And then I'm going to subtract 4 from both sides, minus 3. Hopefully it'll go into brackets, minus 3 plus 1. Which of these answers makes the most sense? Well, a is either equal to -1 or a is equal to 3. But we were told in the question that a and b are integers, and both of them are bigger than 0. So this must be the final answer for a. Right, question 7 looks fun. We're trying to find the gradient of cos xy equals sine x squared plus y squared at the points where x is equal to y. So it says gradient, we're going to do the derivative. But also, we've got x's and y's right next to each other, so that tells us that we're going to be thinking about implicit differentiation. So how can I implicitly differentiate this thing? Well, the derivative of cos is minus sine. That seems to be the easiest step. But once we've done that, the chain rule tells us that we have to times by the derivative of xy. How do you do the derivative of xy? It's now the product rule. So x, leave it the same, times by the derivative of y, plus, write down y, times by the derivative of x, which is just 1. The same works for this other hand side, cos x squared plus y squared. In an ideal world that would be lovely, but we've got to times by the derivative of the inside. In this case it's a bit easier. The derivative of x squared is 2x and the derivative of y squared is 2y with the dy dx on the end. Okay, we've got loads of terms floating around now. Let's get all the dy dx's together. So we've got minus x sine x y dy dx plus, minus y sine xy. And then on the other hand, we're going to have 2x cos x squared plus y squared, and we're going to have 2y dy dx cos x squared plus y squared, which is just about visible on the screen now. Let's get all the dy dx on one side and everything else on the other. I'm going to subtract this, so minus 2x cos x squared plus y squared, minus y sine xy, and I'm going to put this term on this side. So we're going to have 2y cos x squared plus y squared plus this x sine xy and then dy dx. So that tells us that if we divide by that massive bracket, dy dx will be equal to minus 2x cos x squared plus y squared minus y sine xy divided by 2y cos x squared plus y squared, miss the bracket, plus x sine xy. Now, what are we supposed to do with this? Well, we're told that x is equal to y. So let's make x equal to y. Let's turn all of the y's into x's, or vice versa. I'll do x's. So 2x cos, so x squared plus x squared, 2x squared, minus x sine x squared. We'll divide that by 2x cos 2x squared plus x sine x squared, and we'll work out what to do with this. So I'm noticing that there's x's everywhere now. So we can very easily divide by all the x's and we'll get minus 2 cos 2x squared minus sine x squared. We'll divide that by 2 cos 2x squared plus sine x squared. Getting simpler. Not super simple, but getting simpler. From here, I decided to use the double angle formula because I did not spot that the two fractions were the same but with a negative sign. Anyway, just one more step and then we get to the answer. But wait a minute, all these terms are exactly the same apart from the negative sign has changed. So we divide by them, everything disappears, and we get left with the minus 1 that we wanted all along. Huzzah! Now for a vectors question. In this question we've got a square, and we've got OA and we've got OC being given by little a and little c. So if I add that onto the diagram, this vector here is little a, this vector over here is little c. What we're trying to find is the ratio dp to pf, as in the ratio d to p, missed that point, to p to f. In these type of vector questions, we need to find two versions of the same vector, which we could then compare. So the first version I'm going to find is O to P by going this way. I'm going to go up to E and then I'm going to go across. How do we get from O to E? Well, we're told in the question that O to E and E to A is a ratio 1 to 3. So I'm going to go 1/4 of the way up, A, and then I'm going to add on just some part. I don't know how long that is, but just some part of E to B. So these questions usually do a lambda, do whatever letter you want, but that represents some fraction of the way from E to B, which is E to P. What's the actual E to B? Well, we need to continue our journey up to A and then across. So we're going to do the leftovers, 3/4 of A, and we're going to add on C over the top. That's one version. Go to E, O to E, and then some multiple of E to B to get us to P. How else can we get from O to P? Well, why don't we go on the other line? We can go upwards to D and then down to P. How do we get to D? Well, let's read the question. D is the midpoint. Okay, so it's just halfway. So we're going to do half of A and then we're going to add on. Well, we want to kind of go down this way, but we don't know how far. So that's where we get our, in this case, I like to use mu. Again, use whatever letter you'd like as long as it's different from here. But some multiple of D to F. Well, how are we going to do D to F? D to F would be down this way and across this way. So that's down minus a half A. And then across this way, F is the midpoint, so it's exactly half of C. Like this. You can definitely split that down into more steps, but I was just trying to do it all in one go. Now these two are the same. They're both OP, so we can set them equal to each other. So 1/4 A plus lambda of this is equal to 1/2 A plus mu of this. So now comes the lovely bit where we can actually find the values of lambda and mu. We are comparing coefficients now. All of the coefficients of the A's on one side should be the same as the coefficients of the A's on the other side. So on the left, we've got 1/4 and we've got 3/4 lambda. On the right, we've got 1/2. And what else we got? We've got minus 1/2 mu. That's for the A's. For the C's, let's see what we've got. We've got lambda C. So just look, the coefficient is just lambda. And on the right, we've got just this. We've got 1/2 mu. 1/2 times mu. This equation looks a bit nicer to me. So this is going to tell us that 2 lambda is equal to mu. That seems quite useful. And then we can sub it in over here. I guess first off, I'm going to times everything by 4 to make it look a bit neater. 1 plus 3 lambda is equal to 2 minus 2 mu. And then I'm going to substitute in the value of mu into here. So 1 plus 3 lambda is equal to 2 minus 2 lots of mu, so 2 lots of 2 lambda. Then I'm going to minus 1 for both sides, add 4 onto both sides. We get lambda is 1/7. If lambda is 1/7, then that means mu is 2 lots of that, so mu is equal to 2/7. But we're not quite done there. What we're actually looking for, the ratio dp to pf. For this type of question, you have to remember what that line actually is in terms of your working. So in which of these did we use that line? It was this one here, because we went up to D and then down to F. And that's what this vector represented. So that means that mu is the key value. And we're basically told that here, that's 2/7 of the way along, which means that 5/7 is left over. And therefore D to P, PF, is equal to 2 to 5. Basically 2/7 of the way down. So what's missing? 5/7. So 2 to 5 is the ratio. On to question 9, where we've got a bit of differentiation and then a bit more integration. Very, very fun. In part A, we're asked to differentiate cot x with respect to x. There's a few ways that you could go about this. I think what I'm going to do is I'm going to set it up as a fraction, so cos x divided by sine x, and then I'm going to use the quotient rule. So the quotient rule is the one that's given in the formula book, which is nice. So what I'm going to do is I'm going to write down the denominator times by the derivative of the numerator like this. And then I'm going to minus, basically the opposite of that. I'm going to write down the numerator. I'm going to times by the derivative of the denominator. And then I'm going to divide all of that by the denominator squared, like this. Simplify if you can, that's minus sine squared, and that's minus cos squared. And as we all know, sine squared plus cos squared is 1, so minus sine squared minus cos squared must be minus 1. And then finally, what does this give us? It doesn't actually ask for a specific form, so you'd be fine doing that as your answer, but I'm going to write it as minus cosec squared x, just because I can. So let's integrate this thing then. We're trying to integrate square root 1 minus 1 over x squared. A bit funky, as a lot of these questions are. But luckily, we're given the substitution. If you weren't given the substitution, then you might be thinking, well, there's a cosec there, there's a cot there. Those could be two of your candidates. But luckily, we're given the substitution. For a substitution, what we need to do is we need to differentiate. So dx d theta. The derivative of cosec, it should be in the formula book, but I'm going to derive it anyway. So we've got sine theta to the minus 1, and I'm going to use the chain rule. So I'm going to bring down the power, take 1 off the power, times by the derivative of the bracket. So this is minus cos theta divided by sine squared theta. It is in the formula book, and you'd be fine just using that, but I'm going to derive it myself anyway. So what does this mean that dx is equal to? Going to get dx is all of that times by d theta. Let's continue this integral. What we're going to do is we're going to substitute the x in. So we're going to have the square root 1 minus 1 over, and that's now going to be cosec squared theta, because I've changed x for cosec theta. The dx I'm going to change for this whole thing, minus cos theta over sine squared d theta. Which does look messier than it was originally, but it will simplify down, I hope. So 1 over cosec squared is 1 over 1 over sine, so that's going to be back to sine in the numerator like this. The rest I'm just going to rewrite. 1 minus sine squared is, of course, cos squared from our AS formulas, and the square root of that is going to be simply cos. So we're going to get minus cos squared theta over sine squared theta d theta. Now from here, you have to know your identities. Cos over sine, just like in part A, was equal to cot, so this is minus cot squared theta. Now, although that's not in the formula book, there is an identity with cot squared theta that you need to know, which relates it to cosec squared, And because of what we did in part A, we should know what the integral of cosec squared is. If you remember, sine squared plus cos squared equals 1. Then if you divide by sine squared everywhere, you come up with this identity. And this identity is very helpful here because, well, if we rearrange to get 1 minus cosec squared equals minus cot squared, then we're trying to integrate 1 minus cosec squared instead, theta. And believe me, this is useful because the integral of this is theta. The integral of this is theta, and then we're going to add on. If we look at, again, part A, the derivative was minus cosec squared. So if we're trying to integrate that, the answer is going to be this, cot x. And that's going to be plus because this has a minus and the derivative also has a minus. Make sure you understand that idea that if you differentiate something and then integrate that again, you get back to what you started with. Some questions use that idea by having a part A with a derivative and having part B with an integral. So look out for it. I'll add on plus c here, but I'll probably skip it until the very last step for all the next lines. So we've got theta plus cot theta plus c. But that's not the form it's given in. Let's see how we're going to get that. We've got theta, but we've also got theta here. That's our connection to x and theta. So x is equal to this. Let's do it over here. That means that x is equal to 1 over sine theta. Therefore, sine theta is 1 over x. Therefore, theta is sine to the minus 1 of 1 over x, which seems pretty good because, look, it's right here. So that's sine to the minus 1 over x. Cot theta is maybe a bit harder to get. So in order to get cot theta in terms of cosec theta, we want to use this identity. So if we take this line here and we subtract 1 from both sides like this, and then square root both sides like this, then we can use the fact that x is equal to cosec theta to say that cot of theta is the square root of x squared, I'm replacing it with theta, x squared minus 1. And again, that's pretty good because that's exactly what's written. And didn't need any more steps, but there we go, put plus c on the end. Matches up exactly. Happy days. And now for question 10. In question 10, part A, we first have to show that 2x plus 1 is a factor of that cubic. And what we're going to do is we're going to set 2x plus 1 equal to 0, which means that x is equal to minus a half. And then we're going to sub in x is equal to minus a half into the cubic. So 4 lots of minus a half cubed, 2 lots of minus a half squared, minus 2 lots of minus a half, minus 1. I'm not going to go through the details, but that should be equal to 0. For part B, seemingly unrelated, but there is a connection. We need to solve cos theta plus cos 2 theta plus cos 3 theta equal to 0 for the range 0 to 2 pi. Cos theta is good enough as it is, but cos 2 theta we have a formula for. So we even saw that before. This time we're going to use the cos version though, so we're going to write down 2 cos squared theta minus 1. Cos 3 theta, it does have a formula. You're not expected to know it, so let's prove it for ourselves. Cos 3 theta is cos 2 theta plus theta. The cos double angle formula tells us that this should be cos 2 theta cos theta, the opposite sign of the plus there, so minus sine 2 theta sine theta. Using the identity of cos 2 theta, which is 2 cos squared theta minus 1, and using the identity for sine 2 theta, which is 2 sine theta cos theta, we rearrange this, and we're going to get, once we expand, 2 cos cubed theta minus cos theta, minus 2 lots of cos theta sine squared theta. But of course we know the identity for sine squared, which is 1 minus cos squared theta, which means if we expand that bracket, we're going to get 2 cos cubed and then that's going to be plus 2 more, so 4 cos cubed theta, and then minus cos, minus 2 more, minus 3 cos theta. In your question, you may be asked to prove that. Chances are you're not going to get a question that just states it and wants you to use it, but we've proved now. So let's see, put this in, plus 4 cos cubed theta minus 3 cos theta equals 0. Where's the connection to part A? Well, if we make cos theta equal x, then this is x plus 2x squared minus 1 plus 4x cubed minus 3x. And if we do a little bit of rearranging, this is 4x cubed minus 3x plus x, which is minus 2x, plus 2x squared minus 1 equals 0, which I'm hoping should match up exactly to what we've got in part A, which it does. So we know what the solutions are now, or at least one of them. So we know that one of the roots is 2x plus 1. Now you can use polynomial division to work this out, but if you're aiming for top grades, then this method you may already know, or you'll be able to get behind. Think about the fact that 2x needs to be times by something in this bracket to get to 4x cubed. The only thing that can be is 2x squared. And then 2x squared are going to come from these brackets. So we can't possibly have an x term here, otherwise there'd be more than 2x squared. So what we're going to now do is think about how we're going to get minus 1 and 2x. Well, if we minus 1, then we're going to get minus 1 and we're going to get minus 2x. So it factorizes itself really quite nicely. We know that x must be equal to minus a half, again from part A, and now x squared must be equal to 1/2. Let's solve for minus half. So if x, but x not x, it's cos theta equals minus a half, then we want to find all the solutions in the range for which that is true. If we set up our little diagram like this, put down minus half in the diagram, we can see that there's going to be two solutions within that range. And the solutions are going to be 2 over 3 pi and 2 pi minus that, so 4 over 3 pi. So we've got two solutions so far for theta. For this is saying that cos squared theta is equal to 1/2, which means that cos theta is equal to plus or minus, don't forget your plus or minus, 1 over root 2. So if we plot that on the diagram, that's somewhere in here and here, 1 over root 2, 1 over root 2. So we're going to get two more solutions for 1 over root 2 and two more solutions for minus 1 over root 2. Those values of theta will be pi over 4, you can just put that into the calculator, and 2 pi minus that, which is going to be 7 pi over 4. And then if we do for the minus value, then we're going to get 3 pi over 4 and also 5 pi over 4. And those should be all of the solutions within the range. Question 11 is worth 10 marks. So again, in the real exams, they're probably going to help you through it. I'm just throwing it at you as a hard question. See if you can solve it. So we've got two circles. The big one is x squared plus y squared equals 9. And then the smaller one is x minus 9 over 4 squared plus y minus 3 root 3 over 4 squared equals 9 over 4. So straight away that tells us that the origin is the centre of this first circle and its radius is 3. It tells us also that the centre of the second circle, which is B, is 9 over 4, 3 root 3 over 4. And it tells us that the radius of circle B is the square root of this, which is 3 over 2, so half the size. First of all, we probably want to find the points of intersection, and the way we're going to do that, we can't do much without expanding that bracket. So let's expand it. We're going to get x squared minus 9 over 2x plus 81 over 16 plus y squared minus 3 root 3 over 2y plus 27 over 16, and that's going to be equal to 9 over 4. But x squared plus y squared is equal to 9, So what we can do is we can take this x squared and take this y squared and just turn them into 9 by substituting. So 9 minus all of this stuff is equal to 9 over 4. These terms we can simplify somewhat, and we're going to get 27 over 2. And then if I move the x and the y terms to the other side, it will look like this. Times everything by 2, might as well. Makes it look a bit neater, and then also divide everything by 3. Again, it looks a bit neater now. So that expression is very much more simplified, and we've also got this. So we're going to try and connect these two together. Let's sub in x here. So if we do 9 minus root 3y over 3, that's x. Square it plus y squared should be equal to 9. Let's expand and see what we're going to get. So once I've expanded and I've times everything by 9, we get this. These 81s just cancel. If we say that y is not going to be equal to 0, we know that because they're 0, so this line is not going to go through 0, then we're going to get minus 18 root 3 plus 3y plus 9y is equal to 0. So minus 18 root 3 is equal to minus 12y. So y is equal to 18 root 3 over 12. Simplify it, divide everything by 6. Then y is equal to 3 root 3 over 2. Looking back at the diagram, I guess we do need two intersections. I think my diagram is not as good, so I was thinking y can't be 0. But yes, the other solution, it's going to be two solutions. Y is 0, which makes more sense on this diagram because it does look like it's on the x-axis actually. And then y is equal to 3 root 3 over 2. If we now find what x is, we know x squared is equal to 9 minus y squared. So if y is 0, x squared is 9 minus 0. So x is going to be plus or minus 3. And in this case, from the diagram, we know it's going to be the positive version, or you can sub it into this one and you'll find it's the positive version. Similarly, if you sub in the value of y into here, or into here, or into here, wherever you like, you'll get that x is equal to 3 over 2, whichever one you put it into. When I write down these two coordinates here, you may notice that if you look at the midpoint of the x's and the midpoint of the y, then you get the point B, the centre of this circle. So actually this line that we found goes right through not only the two intersections, but also the centre of that circle. And that's going to make finding the area of at least this half quite easy. So let's break it down into two sections. We'll call it R1 and we'll call it R2. R1, as I say, is simply just half a circle. So half times by pi r squared, where the radius is the radius of the smaller circle, which we found to be 3 over 2. So half times by pi, 3 over 2 squared, 9 over 4. So 9 pi over 8 for region R1. For region R2, we're going to be needing to do something to do with sectors. So this time, we're looking at this sector here for R2, and then we want to take away the triangle in there. That's going to give us the segment, that's going to give us the final answer. What we don't have yet is this angle in here. Right, I made a quick second sketch which looks a bit more appropriate for this sector, given that these two coordinates lie on the same horizontal line. We know what the size of this line is because it's simply the radius of the circle, which we know to be 3. And because it's a sector, this is also the radius, so that's also 3. Which means if we think about this little triangle in here, we know that the length is 3 over 2, and we know that the height is 3 root 3 over 2. Which means that if we say that let's do cos of theta is equal to adjacent over hypotenuse, then we're going to get that cos of theta is equal to a half. Therefore, theta is equal to pi over 3. If you've got pi over 3, then we can use our radian formulas to work out the area. The area of the whole sector will be half r squared theta. And then the area of the triangle that we want to take away, which looks very similar, but that is a bit rounded, is half r squared or half ab sine theta, so sine pi over 3. So simplifying things, this is going to be 3 over 2 pi, and then this one is going to be 9 over 2 times root 3 over 2, so 9 root 3 over 4. Put it all together, the area of the segment, which we called R2, will be the area of the sector, subtract the area of the triangle. And then finally putting it together, the area of the shaded region will be equal to R2 plus R1. So from before, R1 was 9 pi over 8. And to that, we're going to add R2, which is this. And then to try and put it in the exact form, first I'll take a factor of an 8 out and go from there. So 9 pi, this one we need to times by 4, 12 pi. And then this one we need to times by 2, 18 root 3. Which we can then take out a factor of, well, I'll first add these two together actually. 21 pi minus 18 root 3. And then I'll take out a factor of 3, 7 pi minus 6 root 3. And hopefully that's what it's given. 3 over 8. Oh, it's A and B. So basically A is 7 here. And then B is going to be 6 from here. Wonderful. We're almost there now with only 2 to go. Question 12 is the expansion of 2 minus 3x to the power of minus 5. And we're going to use that to find the expansion of 2 minus 6y plus 3y squared to the power of minus 5, which is a bit wackier. Let's consider how we're going to expand this. First off, there's a 2. We don't want that 2. The formula doesn't have that 2 in there. So what we need to do is we need to take it out. So 2 to the power of minus 5 times 1 minus 3 over 2x to the power of minus 5. Once there's a 1 there, we're happy. We can use the formula as standard. Going to get 2 to the power of minus 5, we can just work that out, 1 over 32. And then this is going to be 1, always starts with 1. We're going to add the power, minus 5, and then everything that's xy. Then we're going to add the power, try and take away 1 properly, divide it by 2 factorial, or just 2, take the x bit and square it. And then we can continue the process. So minus 5, minus 1, minus 1 again. This time divide by 3 factorial, or 6. Get the x bit and cube it. The part of the question below only talks about the y cube term, so plus dot dot dot, I'm not going to find any more. I'll quickly put that all in the calculator to work out and see if you get the same answer. We've followed the hint and we've considered the expansion for this, but how are we going to get the expansion with the extra terms in? Do you see the connection? We can rewrite the bracket in the question as this. If you expand out the minus 3, you get minus 6y, you get plus 3y squared. So it's the same bracket, but this time we're going to treat this as our x. So what's the expansion of this? It's going to look very similar to this, 1 over 32 plus 15 over 64. But I'm not going to write x, I'm going to write 2y minus y squared. 135 over 128, I'm not going to write x squared, I'm going to write 2y minus y squared. And then finally, I'm not going to write this as x cubed, 2y minus y squared cubed is what I'm going to write instead. And what are we considering? We're considering the y cubed terms. So where's a y cubed going to come from? Well, not here. Not here, that's y. Not here, that's y squared. Are we going to get any y cubed terms from here? Yes. Y times y squared is y cubed. So the coefficient of y cubed, we're going to get 135 over 128, lots of. What's the term going to be here? Well, it's 2y times minus y squared, so minus 2. But also y squared times y. When you square a bracket, it happens both ways round. So I'm going to do that times 2. So this is the bracket coefficient. This is the coefficient from the y cubed inside. and then this is times by 2 because there's two ways of getting it. Could we get y cubed over here? If you cube a bracket, is there any way of getting y cubed? Definitely. Y times y times y. So we're going to add on 945 over 256 times by 2 cubed. There's no other ways of getting y cubed. Y times y times y is just the first thing in each bracket. So there's no need to times it by 2 or 3 or anything. And from here, pop it in the calculator. Let's see what we get. And we get 405 over 16. And Wolfram Alpha agrees, so it must be right. We've made it. Last question, question 13. And it's the trapezium rule. But a tricky trapezium rule. We've got n strips, but I'm not telling you what n is. And we're trying to estimate the value of e to the power of x. Now, of course, we know what the integral of e to the power of x is, but that's not what I'm testing. What I'm testing in this is how you apply the trapezium rule to something a bit strange. E to the x looks somewhat like this. And then let's put 0 there and 1 there. I've told you it's n strips, but I haven't said what n is. So we're going to break it down like this. N trapezia, somewhat like this. So what you've got to work out is what's the starting point, what's the ending point of the trapezia, and then find e to the power of that. If there are n strips in total, that means that we can use the formula h equals b minus a over n to find the width of each strip. That's given in the formula book. I'm going to get 1 minus 0 over n, or 1 minus n. So this little guy is going to be 1 over n, and then 2 over n, 3 over n, all the way down to n minus 1 over n. So those are the x values. But the formula, if I write down the formula, it's 1 half h, y0 plus yn plus 2 lots of y, 1 plus 2 plus y dot, like that. So that's the formula given. So y0, yn, these are all y's. We've got these are the x's. So we need to do e to the power of all these x's. So, therefore, putting it all together, this integral not equals, but approximately equal to 1 half times h, which we know is 1 over n, times by, nice big bracket please, y0 is going to be e to the power of the first value of x. It's going to be e to the power of 0. Just 1. Yn is the last value. It's going to be e to the power of this, e to the power of 1, which is e. And then we're going to add on 2 lots of everything else. So e to the power of 1 over n, e to the power of 2 over n, e to the power of 3 over n, etc. And then we're going to end with e to the power of n minus 1 over n. So the very last term before we get to 1. Okay, it doesn't look very nice, but I'm going to show you it's correct. 1 over 2 times 1 over n is 1 over 2n. That seems quite good because that's the answer down here. There's a 2n. And then what else are we going to get? We're going to get 1 plus e plus 2 lots of all of this. What is this? We've got to see it as a geometric sequence, but you didn't see that coming. That is a geometric sequence because every time you are timesing by e to the power of 1 over n. Because remember, when you times by e to the power of 1 over n, you add the powers. So that's a geometric sequence, and we can use the summation formula for a geometric sequence. That's going to be a, which is the first term, just there, 1 minus r, usually r to the n. So r is e to the 1 over n. That's what we're timesing by each time. The n in the actual formula, which is maybe not the same as this n, is how many terms do we have? How many terms do we have in this case? If you count them all, we've got n minus 1. And then we divide that by 1 minus r. In our case, r is, again, what we times by each time, common ratio, which is this. Again, it's looking pretty good because the final answer has a 1 minus e to the power of 1 over n, which is exactly our denominator here. If we keep going, we're going to get, this is all one fraction, so what I'm going to do is I'm going to make this all one fraction. To make it one fraction, I'm going to do 1 plus e times by the denominator and then divide by the denominator like this, because then we can make the fractions work quite nicely. And then we're going to add 2 lots of I'll expand that out. So e to the 1 over n times 1, and then minus e to the 1 over n times by e to the 1 over n to the power of n minus 1. What an expression. Same denominator. I can assure you this does simplify. So because this is two powers, same base, timesing each other, we're going to add the powers. But if we add 1 over n to n minus 1 over n, we're going to get 1 over n plus n minus 1 over n, which is n over n, which is 1. So this is just e to the 1 over n minus 1, all over the same denominator as before, like this. So n over n, which is 1, so e to the power of 1, not 1, or just e. If we continue from there, let's expand this out. We're going to get 1 plus e minus e to the 1 over n minus e times by e to the 1 over n. And then we're going to add 2 lots of e to the 1 over n, and we're going to minus 2e. Still divided by the same denominator here. From there, we're trying to simplify as much as we can. We've got 1 on its own. We've got e minus 2e, so minus e. We've got minus e to the 1 over n plus 2, so now plus e to the 1 over n. And then we've got minus e to the e, and we've got minus e to the 1 over n, all divided by the same denominator. And from there, it could just be factorising it. It could just almost be copying the answer or expanding the answer and seeing if it works. You'll notice that if you times 1 by what's given, then you get 1 plus e to the 1 over n minus e, and then minus this term. So it's exactly what it wants. A few ways of actually proving it in the end. And then it goes into the brackets exactly as we want for our 8 marks and final question on the paper. Well, there you have it, another set of questions complete. Hopefully some of those got your brain in gear, get you thinking nice and tricky. Good luck with the rest of your revision and good luck with your exams.